welcome back to another episode of Coding Wizards. Today in this episode we're going to be going over machine learning, and the type of machine learning that we're going to go over is a pretty basic one called linear regression. So as you can see here, we're in Python. I'm in a file called machine learning linear regression.py, and I have some import statements here. There's two black boxes, one here and one here, just to cover up my name because these are file paths. So first of all, for import statements, we have from sklearn, which is the machine learning library we're going to be using. We're going to input the linear model for linear regression. From pandas, we're going to import pandas as PD for data frames and all that kind of stuff. Input numpy as MP for arrays and all that stuff. Import CSV because we're going to be importing a CSV file. From Tkinter, we're going to import everything. This is what this means in the terms of import statements, this little like star thing. And this will just essentially allow us to build some interfaces later. And then from sklearn, we're going to import metrics, which will allow us to test our data. So first of all, we have a constant here called data frame head, and this is essentially how many indexes do we want to have our dataset trained off, because as you can see here, for the train values, it takes only the df head, which is like the x amount of top bits of the data frame, and then I just have a constant here. So I could put 100 here and it would evaluate as the same, but I just like this, so I can change it to like 3000, and then both of them will change. I'll just set this really high right now so it will capture all the datasets values. So first of all, we need to prepare our data for the machine learning. A lot of the heavy lifting done with this is done by sklearn, so you don't have to do that much actually. So we're going to have a data frame, and it's going to be equal to pd.dataframe, so pandas data frame type. And then we're going to use pandas to read the CSV instead of having to go line for line. Pandas are so good. And you can read local CSV files just by getting the right file path, but this one is a online machine learning database CSV file. So this is essentially just leads to a repository of text that is a CSV file. So we can just import that. And then what we're going to do is we're going to take the data frame columns. I'm going to name them sepal length in cm, sepal width in cm, petal length in cm, petal width in cm, and iris type. So as you can see, we have the data frame up here and it has different columns. It has 4,000 lines of each of the entries. So essentially, there's 4,000 different irises in here because this is an iris data set. And iris is a type of flower. So as sepal length, sepal width, I'm not sure what those are, but they're probably some plant part. And then petal length and petal width, and then it also has the iris type. I believe there are 3 iris classes, 3 iris types. We won't be using the iris type today, but later I also did a logistic regression model which takes into account the iris type. It takes some other variables and then tries to guess the iris type. Now we need to prepare the x-train values. So these are the values we're going to give the thing. We're going to say, okay, given these values, I want you to find the y value. Make a model that does that, because what sklearn is doing here with linear regression is that it's trying to fit our data onto a line. So it's really trying to draw a line of best fit. And it does this by we give it data and we say, okay, we want you to fit this x to a y and create a linear line, linear regression, that fits this data. And it will try its best to, but of course, all these points will definitely not be collinear, so you can't just draw a line and have it 100% accurate. Which is why what it's going to try and do every time, it's going to try and minimize the error essentially between that. And this just uses a mathematical formula, and it keeps doing that until it is able to actually get something that fits your data that you gave it. Now, I don't have any y train values, but y test values. But what I could do is I could go, okay, I want to create some. Yeah, I'm checking. Sorry. Yeah, I don't have any test values in this, but what I could do, and I'll show you this to you in the logistic regression one, is I can go, okay, I want to take all the results from the data frame. So I'm going to take, for x, I'm going to take these to the sepal length and the sepal width. But instead of just taking the head, I'm going to take all of them. And then for the y, I'm going to do the same thing, except that I'm going to take the data frame. I'm only going to take the petal length in cm. And that's that. So also, I just have to mention, instead of trying to fit it on like a two-dimensional linear line, it will be creating like a three-dimensional plane as a line because we have more than one x value. It's essentially, given these values, can I find the y value? And you can have one simply by doing this. You just put a comma and then you put the names of them. Make sure you have two brackets here though, so it becomes a matrix. Because the later for fitting the model, which is essentially saying, okay, I have these values, I want you to create a model for it. You need to have a matrix here in the x train values. So I could add more and it would become a even more dimensional thing, but I'm just going to stick with sepal length in cm and sepal width in cm. So we get all this data, and now we have to create a new model. So I'm going to create a variable called model, and I'm going to set it equal to the linear model, which is from sklearn. I'm going to linear model.linear regression. So for linear models, we're going to choose linear regression here, and then we're just going to fit it. So we're going to model.fit x train values, y train values, which will make. So now this model is actually like a fit model to our data. And then what I'm doing here I'm printing the model coefficients. So as you can see here, these are essentially the slopes of the line, so we're going to print those. And then I'm going to set m, or slope, in the equation y equals mx plus b, where b is the slope, b is the y-intercept, m is the slope, sorry, and then there's x and y. But since we have 2x, essentially the equation is going to be y equals m1 times mx, x1 plus m2 times x2 plus b. So I'm just displaying these two coefficients here, and then I'm setting the 0th index, or essentially the first index, onto m1, and the first or second index, first for a computer, second for us, onto m2. And then I'm going to set the y-intercept equal to the model.intercept. I'm setting these all to floats because these are floats, these aren't just integers, just to make sure that's all good. So then what I'm going to do is I'm going to create a function which, given an x1 and an x2, so essentially given a sepal length in cm and a sepal width in cm, it will do the calculations with the slopes, as you can see, and the formula I provided. So essentially we have like y equals mx plus b, of course, with another x that has filled out slopes, so y equals 3x plus 9, whatever, that kind of thing, except we have multiple from the machine learning in the equation now. And then you can ignore this. This is just a Takinto interface. Um, it's not that important, but essentially I was able to create a little pop-up window where you can put in these values, these x1 and x2 values, and it would give you something. So we're going to say, okay, so I'm just going to look at the data frame right now, and it says, so yeah, we're trying to, our target goal, we're trying to find, based off sepal length in cm and sepal width in cm, the petal length in cm. So currently I have an iris here, which has a sepal length of 5.7, a width sepal width of 4.4, and a petal length of 1.5. So keep these numbers in mind, and we're going to try and use the model we have from sklearn to predict this data. So if we just go down here and also ignore this root main loop thing, it is also part of the Takinto interface. Essentially, you create a bunch of things and using objects Takinto gives you for the interface, and then what you do is you keep running those things over and over again with loops. You keep looping these so it keeps it on the screen. I'll go into some of this later, but essentially you're creating a frame and labels, which are text, and entry boxes, and then I have a function here to calculate it from the thing. But yeah, fairly simple, but yeah, Takinto is a very good thing to use for interfaces. So we're just going to print the value of the, say the sepal length was 5.7, and so we're going to use the equation function, and we have a sepal length of 5.7 and a sepal width of 4.4. And we're going to say, okay, well, what's going to be our petal length? Now, if we run this again, we get 1.7129. So this is not actually 1.5. And the reason it's not like this, it's because there are like 4,000 different irises in here. So its best guess on a iris that has a sepal length of 5.7 and a sepal width of 4.4 is 1.7129. So it can't really get the exact number often because to get the, because for example, there might be another petal with the same kind of thing except with sepal length of like 2, right? And so it doesn't know which one to pick given our data. So I'm relatively happy with this level of accuracy. It's really hard to measure accuracy though with something that has a consistent, like a consistent data output or a quantitative data output. Because qualitative, you can say, okay, is this thing yes, or is this thing no? And you can categorize. If you got yes, then you did it. If when it was if the answer was yes and you got yes, then that's correct. If the answer was no and you got no, that was correct. If the answer was yes and you got no, then that's incorrect. And you can kind of classify that, and you can build like a percentage on how many you got right. But because it's a quantitative data, we're going to say, okay, if we're trying to use the old way we would measure accuracy, we would go, okay, well, the petal length is 1.5. Is it 1.7129? Like, is it this number? Of course it's not going to be this number. Nothing is going to be this number, especially with all the decimals here. So what you need to do is assign like a level of accuracy, a percentage of accuracy, and if it's within that zone, then it will say, okay, well this is correct and this is incorrect, and then you can kind of get a percentage accuracy and stuff like that. But yeah, overall, this is just linear regression. Not it's multiple linear regression actually. Not that exciting, but it is quite fun. Yeah. One interesting experiment. We'll say if what if we only train it off 10? So we only train it off 10 pieces instead of the 4,000. We'll get a different result, and we'll get different coefficients, much different coefficients as you can see. But it still gives us something like 1.65. If we train it with 1,000, we might get, or we get roughly, yeah, I think we get exactly the other one here, which is kind of interesting. I'm not actually sure how big this dataset is. I think it is fairly big though. It is definitely, yeah, if we run 100, it's also different, and I believe this is actually the same as that one. So it might be a lot smaller than I actually thought, but either way, as you can see, with an increase of data points, the accuracy of it increases. For example, if I fed it one data point, it'd give me like 1.4. If I fed it two, it'd give me a more robust stuff with actual slopes. If I give it 3, it's going to give me something like that. The reason these don't have slopes here is because the intercept is just 1.4, because it's saying, well, okay, I don't know if there's actual change because I only have one data point. So I'm just going to say it's always 1.4 because I have nothing else to show that it isn't always 1.4. The only thing I have is 1.4. If we run 5, you can see it's a lot different. We do 20, it's start changing a bunch. And then good thing about, of course, there's not actually this many data points in this actual data frame or indexes. But if you go over the maximum, it will just do the maximum. So you can just put in like 9 just lots, which obviously you don't have that many data points, but it will still give you the same result as if you put in maybe a lot less, but still enough to be above the maximum. So yeah, this is really easy to do in Python and extremely fast, takes almost no time. So yeah, the main magic is the fitting the model and then getting the coefficients and the intercept, and then so yeah, and then getting like the linear regression model, and mainly it's sklearn that's doing all the um, like hard stuff, because sklearn has like thousands of lines of code to try and do this kind of stuff, and you just have to put in one function, and that does it all for you. So yeah, I would definitely recommend using these libraries, and I would also recommend understanding the mathematical principles behind these things, somewhat, as much as you can, because I know I can't understand all that much about this. But when you do know about that, there's often different options. For example, in SVM support vector machines, there's stuff like gamma and C, and you can kind of understand how those work. And if you do, you can tinker with the settings of the model to be able to create a more accurate model that predicts your data better for your given data set. And with learning the different machine learning types, you can say, okay, I want to use this one for this project because I think that this one will work the well. Maybe because you don't have a large data set and you think that this would do the best job even though it has a small data set. or you just think that the data is represented in such a way that it's maybe not good if you use linear regression. As you can see here, one of the big faults of linear regression is that it's linear. So I have something like the first number, the sepal length, is going to give me a positive slope. So if I enter something with 50,000 sepal length, of course nothing will have that. It will say, wow, this thing must have a dumb amount of petal length too, because this is sepal length is a positive thing, and we're just gonna multiply this by this to get something, and then add it with the result of multiplying 4.4 with negative 1.332, and then adding the slope, and I should actually print the slope. But yeah, that's one of the big faults with um, linear regression, or honestly, lots of different things like logistic regression. If you're trying to find a value like this, it gets kind of weird. But what's interesting with support vector machines is that there's areas or decision trees. There's much more. There's a different way of thinking, so it's not just fully linear. Like, can we put more of this into something? Like, there's an example where I was looking at this was also on the machine learning database, but I believe machine learning repository. There was something on wine and how um, different factors, like different chemicals in wine, affects the quality of the wine. And one of them was like, okay, well, it says pH is a positive indicator, like a positive slope, just like this, that putting more pH in wine means that the wine's better quality. So does that mean if I put something that would kill someone, like 10,000 pH, something off the charts in wine, it would be good? No, of course it wouldn't be good. But the system thinks it's good because it's linear. So if I just quickly grab the intercept here, auto.intercept, and print it, you can see the intercept is negative 2.5 something, but yeah, that's also part of it. But as you can see, with actual real results, it's able to predict data quite easily, and uh, linear regression only works with um, quantitative data, not qualitative data, which means that it's like numbers. It can be a theoretical infinite amount of possibilities to produce quantitative data. And I think next time I'll look at logistic regression since I've been talking about it a lot. And it takes quantitative data to create qualitative data. And it works quite well in doing that. But anyway, thanks for watching, guys. This has been in Python, machine learning, linear regression. And yeah, hope you enjoyed it. Thanks. Bye.